Okay, thank you. Thank you very much. So it's a great pleasure and honor to be here in this meeting honoring Menahem. So I want to talk about, my title is kind of vague. Right, so some techniques. I did talk with Menahem about it some years ago. I want to basically describe, there won't be any theorems. There will be only definitions. Okay, wait a second, it's not working. It's stuck. Oh, you have to go to the left, right? Yes. Okay, that's why.
No, it's not.
No, it's you press the left key. I see. Okay, so basically the standard. Okay, so it's about iterated forcing. It's I guess everyone in this room knows very well. The standard ways of iterating forcing are basically concentrated on the notion of support. So the first iteration by, I guess, Solovey and Tenenbaum was finite support iteration of CCC forcings. Then later, people started looking at countable support, revised countable support. Of course, there are many other. I won't go into that. We are interested in preserving some properties of the pulses that we are iterating, primarily preserving cardinals. So I highlighted the three most common techniques and the preservation they do. And typically, we do an iteration of a certain length kappa. And if we arrange things that the pulses that we iterate are small, then we have the kappa chain condition. So we'll preserve cardinals above bigger than equal kappa as well. Okay, now all these methods have kind of inherent drawbacks. Finite support of non-CCC forcings actually is going, non-trivial forcings collapses Aleph 1, so it's not suitable for what we want to do. Whereas the proofs of the preservation theorems for proper and semi-proper forcings using countable support or revised countable support depend on diagonalization, where the size of the support is countable, and then you do countable diagonalization, and this is what you use to show that omega 1 is preserved. Now, the problem is, okay, now I also wanted to mention that there are some other notions of support by Sakharon and Roslanovsky, uncountable support iteration. I'm not going to give a full history, just mention a few names. Typically, if one is interested in preserving cardinals, for larger supports, one has to require that the posits, the iterants, are sufficiently closed. So overall, the kind of standard methods are quite limited if we want to preserve more than one successive cardinals, like omega 1 and omega 2. Unless, of course, we arrange the omega 2 chain condition, but then that we cannot do some more sophisticated applications. Okay, so then maybe some 5 years ago, Itai Niemann introduced a new method, which from what I understand was inspired by Bill Mitchell's work on the approachability ideal on omega 2. Well, and actually there was, I guess before that, Bill, correct me, the Mitchell-Friedman posted for adding a club in omega 2 with finite conditions. So Niemann took this further, and he defined a different notion of iteration where you don't concentrate on the support, but you actually put on models that control the so-called working parts. And I'm going to give some definitions in a bit. Now, the advantage of this method is that you don't do diagonalization. And so you have some hope of preserving more than one cardinal, like omega 1, omega 2. Now, Niemann first did this for just the kind of standard iteration, standard proper poset, notion of proper, using finite support, but with side conditions which were elementary submodels of V kappa or H kappa, where kappa is the length of the iteration. So that's the first. Then he generalized this to posets which preserve, certain posets which preserve omega 1 and omega 2. And there he needed, actually even for the usual proper posets, he needed side conditions of two types, countable in order to preserve omega 1 or to guarantee properness, and transitive, which were initial segments of V kappa, so some V alphas or so. But for the more general posets, which, well, I should not say more general. I mean, for the posets that preserve more than one cardinal, let's say omega 1 and omega 2, you need, well, two types of nodes plus the transitive node. So you need countable nodes or models in order to guarantee that omega 1 is preserved, and then you need models of size aleph 1 in order to guarantee that omega 2 is preserved. And then you need some transitive nodes, which was not clear, and actually we will get rid of the transitive nodes in this lecture. There were also some non-elementary nodes, which this part was kind of mysterious, at least for me. So anyway, so with this, Itai was able to get many interesting applications, and I guess the most fascinating is a solution to the Baumgartner problem, namely the consistency that all aleph 2 dense sets of reals are isomorphic, together with continuum aleph 3. So this was kind of beyond the limit of the methods that we had known before. So this is maybe the most spectacular new application. I should mention, although it's not quite related to what I'm going to talk about, there is some work of Aspero and Motta using systems of countable elementary submodels, so not a chain, but a symmetric system of countable elementary submodels. So what they were able to do is get some consequences of the usual proper forcing axiom together with continuum arbitrarily large. But they were not using uncountable models, although I think now Aspero has some new approach, I mean, incorporating uncountable models, but I don't know much about this. Okay, so let me say what I want to do in this lecture. So basically, I want to redo Niemann's method. For my main motivation was in order to iterate generalizations of semi-proper posets, which Itai's method did not seem to be able to do. As it turns out, if you do things in the right way, then even the original construction is much simpler. So I'm not going to do the semi-proper version, because that would be just too many definitions, but I'm going to do the two cardinal proper version, describe the basic definition, and then I will say something about what are the changes you need to make in order to incorporate the non-proper version. So I should say that Moti and Menahem have Moti, Menahem, and then Moti on his own have a different way, which I must say I don't understand, but hopefully they can, or Moti can explain this. Okay, so so just to remind ourselves of what is proper. So first, this is the usual definition of a generic condition for an elementary submodel. Here I don't restrict the size of the model, and I say that the condition, so the poset is Q, theta is a sufficiently large regular cardinal, M is an elementary submodel containing Q, and the condition is MQ generic if. Now you can always form the model M of G, M square bracket G, namely you take all the names in M and you interpret them using G. That's, I mean, people think you can always, you can do this only if Q is proper. No, you can always form the model M of G, but sometimes you may get objects from the ground, new objects from the ground model. So you say that the condition is MQ generic if it forces that the generic extension M of G has the same, I mean, its ground model is M, namely its intersection with the ground model is M. It doesn't add new ordinals or new ground model objects. And then, given a collection of elementary submodels, we say that Q, collection S, we say that Q is S proper if for every M in S and every condition in M, there is a stronger condition which is MQ generic. So it's the usual definition. I think S proper, maybe the word is not the most fortunate because it was used to denote other things. But if S is the collection of all countable models containing our Q, then we just say Q is proper. Now, of course, we will be interested in posets which are proper for larger classes of models. Okay, now, this is something that I guess should have been done or could have been done when the notion of proper was defined, but it was probably would not have been clear why would you do that. So as a kind of warm-up, let's define, so let's assume that we have a proper poset, and theta, you don't have to specify theta, it's just sufficiently large, maybe 2 to the size of the poset plus. So you have all dense sets inside H theta. You have Q and you have all dense. Okay, so now you make a poset, starting from Q, you make another poset, which I call M of Q. What is M of Q? Well, it's a pair. Conditions are pairs. P is a pair, MP, WP, where MP is a finite chain of countable elementary submodels containing, I guess here I can, we just, if I don't say all models contain Q, and WP is the working part. And so you require that the WP is generic for all the models on that chain. So it's a finite chain, and a working part is a condition generic for all the models on the chain. And the order is, you're allowed to add new models, and you're allowed to strengthen the working part. So again, it's maybe not clear why would you look at this, but you can. And now there is a little lemma which you can sort of extract from Niemann's first paper. It's basically saying that if Q is proper, then M of Q is proper. But I made it more precise. So first, if you have a condition and which belongs to a model, then you can put that model on top. Well, that's kind of clear because your condition is a chain of models. That whole chain, it's a pair, a chain of models plus a working part. Everything is inside M. So you just put M on top, and you strengthen the working part to something which is generic for the model. You can because the poset is proper. So that's the first part. The second part requires a little bit of work. It says that if, basically, I mean, it says that M of Q itself, if Q is proper, then M of Q is proper, but I state it in a kind of more precise way. Basically, when you have a condition it's a chain, or it's a pair, a chain of models and a working part. If a model appears on the chain, then you would like to say the condition is generic for that model. Now, strictly speaking, you cannot, because the model doesn't contain the poset. Remember, the original poset is Q, so the new poset is chains of models together with working. So you go to a bigger theta. This is the usual thing, so I won't spend much time on that. So, but morally, I mean, putting a model on this as a side condition, it imposes that the whole condition is generic for this scaffolding poset M of Q. And this is a little lemma which I think, it's very easy to prove if you think of it. I mean, if you think that that may be relevant. Okay, so, and this lemma contains the essence of this new method, even though, I mean, you don't literally use it, but you use some version of it. But I mean, I stated it here so that if there is something that you remember, then it should be this or some generalization of it. So now let's use this as a kind of inspiration for defining the kind of two cardinal proper posets. So so basically now we want to include in our chain models with not only countable, but size aleph 1. Now, if you think about it for a second, if you have two models, M and N, let's say N is an element of M, and this is of size aleph 1, this is countable, and if you have a condition which is generic for both of them, then it's generic for the intersection. This is straightforward to see. So basically, if we're going to have chains of models, then our chains should be closed under intersection. If we require the working part to be generic for all the models in the chain, then when you put two models, then then you should also put the intersection. Notice that if N and M are of the same size, say either aleph 0 or aleph 1, then the intersection, I mean, it's transitive, right? So it's kind of, if you had only models of one type, those chains were already closed on the intersection, but that was kind of trivial. Okay, sorry. Now, so in other words, what we need is we don't take all models of size aleph 1, we take only models which are internally clubbed, which means you can write them as an increasing union of a continuous chain of countable models which are all in N. You don't require that the chain, initial segments of the chain are themselves in N, just that each member of the chain is in N. And I think this was already mentioned. Okay. So now we have two types of models we want to use, countable and internally clubbed. Again, the reason why we want to use internally clubbed is because of this observation that we want to close under intersections. So now here is the kind of straightforward generalization of the scaffolding poset. We're starting from a poset Q. We define M. I use the same letter, actually. I don't know. OK, so this should be boldface M of Q. There's already a first type. So what is it going to be? Just by kind of analogy. So let's use finite epsilon chains of models in C union U. C is for countable, U is for uncountable. OK, not very imaginative. Closed under intersections. Oh, sorry. This is before the. I'm not defining the scaffolding. I'm defining just the pure side condition. Sorry. And then we will add the working part. So this is the first thing you do. In the case of just one type of model, just let's say countable, that was kind of trivial, finite chains of countable models. So here you have finite chains of countable or internally clubbed models closed under intersection, and the order is reverse inclusion. And this, sorry, so I will come to the scaffolding in a moment. So now you have kind of little proposition which is a little bit less trivial to prove, but not very difficult. Basically, you have a condition, it belongs to a model, then you can add that model on top. Now, if the model is uncountable, that's all you have to do. If the model is countable, maybe you have some old uncountable models, so you have to close under intersection with the old models. And you have to check that what you have is still an epsilon chain and whatnot. So this is the first part of the proposition. The second part says that, OK, now suppose you have a condition, so it's a chain closed under intersection, and you have one model on the chain. Now, if you intersect the chain with a model, that's some subchain. It's not an initial segment. It's just kind of some pieces of the chain. And if you take that, so that's inside M, and you extend it to a stronger condition which is inside M, then you can amalgamate with the whole condition. So this is kind of version of the well, actually, it's exactly strong properness, right? Which Bill calls strong properness. I mean, you can take this almost as a definition, but it does imply the usual properness. So the point is that the pure side condition preserves two cardinals, omega 1 and omega 2. OK, so great. So let's now add the working parts. So now we have a poset Q. Now, the problem is I don't want to tell you what is Q. I mean, we have to find some conditions on Q so that this definition gives us a reasonable poset. So we want to have an analog of the situation we had in the just one type of model case. So OK, so what are the conditions in M of Q? Well, so it's a chain closed under intersection. So it's a pair. P is a condition if it's a pair, MP, WP, where MP is from the pure side condition. And WP is generic for all the models on this chain. And the order is what you expect. So you're allowed to add more models, and you're allowed to strengthen the working part. OK, so now you would like to have an analog of the lemma we had for just countable models, right? So we would like this scaffolding poset to be such that whenever you have a condition which belongs to a model, you can add that model on top. Which means you should be able, so you have a condition which is a chain of models, and the working part belongs to a model. You can add that model to your chain closed under intersections. Then you have to extend the working part to make it generic for that model. The problem is, it's not only that model. You have also some intersections with models that you had before. So just assuming that you have generic conditions for, in other words, that you are C union U proper, it does not guarantee that you can find this lemma. So basically what we do, we cheat. We cheat in the sense we just make this our definition. In other words, and this is, in fact, the thing that is missing in the case when you have two types of models is that you cannot find, you have a chain and a model on that chain. You have the piece of the chain inside the model. You have a condition inside which is generic for that piece of the chain. You need to extend it to a condition generic for all the models on the chain. In the case of the usual proper, that was straightforward. You just do it one at a time. You keep hopping from one model to the next one, getting more and more generic conditions. But here, your chain is not transitive. So you cannot do it unless you just impose something on Q. So we just make this our definition. Now you say, well, is it a reasonable definition? Of course, we need to have enough posets that satisfy these properties so that we can do something interesting. So, but basically, we make a definition so that we have the exact analog of the usual proper case, the scaffolding. Okay, but I call it naively omega 1, omega 2 proper because, as you will see in a moment, it does not work. I mean, there is something missing. So that's, and here is a version of the Mitchell-Friedman forcing for adding a club with finite conditions. It's the shortest one to write. I mean, this is eta-ice, although there are various versions of this. So what is it? You do it on omega 2. Okay, so you add a club in omega 2 with finite approximations. So what are the approximations? To conform with my notation, so they are going to be pairs of, this theta should be omega 2, actually. Because, oh, I did say theta, let theta be omega 2, so that's fine. So it's a chain, it's the side condition part, but together with a function, dp, to each model on your chain, you assign a finite set, which belongs to the next, actually belongs to all the models which contain our model. And basically, this function tells you the next model, I mean, the content is that the next model, so you're going to be extending your chain, so you'll be adding more models. So if you put M, then there is D of M, dP of M, that's a finite set. So the next model you insert has to, if it contains M, it has to contain this finite set. So that sort of limits the models that you are allowed to put. Once you put M, the next model should contain dP of M. Okay, so and the order is you're allowed to add more models and you're allowed to extend dP, which means, remember, dP is to each model assigns a finite set. So you're allowed to increase that finite set. Now, the point is that this pose set is, I call it M2 for some historical reasons. It adds a club in omega 2 with, well, you can call this finite conditions, but the main important aspect, part is that this pose set, the generic club does not have any infinite subsets in the ground model. So you are able to add the club in omega 2 in such a way that it has no infinite subsets from the ground model. Now, if you could iterate this up to, say, some inaccessible cardinal, if you could iterate this up to some inaccessible, say, inaccessible cardinal, then you keep adding clubs which have no infinite subsets in the ground model, well, you run into trouble with club guessing. Because I remind you that Shelach's club guessing at omega 2 says that you can, to each ordinal of cofinality omega, in omega 2 you can fix an omega sequence such that every club in omega 2 contains one of these, in fact, many of these sequences. So the point is, if you could iterate this pose set, then this club guessing sequence will appear at some stage, and then at the next stage you add a club which has no infinite subset of the ground model, so it avoids this club guessing sequence. So in other words, you would violate club guessing if you could iterate this. When did I start? I have 20 minutes? Okay. Okay, I should speed up. Okay, so now let me tell you what is the general setup. And here is going to be a bunch of definitions. But the point is, the definitions are the main thing. I mean, once you make things right. So a structure is a model, transitive model of set theory together with a unary predicate, which is going to be our kind of bookkeeping function. And if you have a structure, then we call it A, then EA is the set of initial segments of the structure which are elementary in the whole structure. It may be empty, but typically it's not. I mean, the case we're interested in is we're going to start with an inaccessible cardinal, so it's going to be non-empty. In fact, it's always closed. And we define the function next of alpha. This is the next element of EA above alpha. OK, another thing, we have the closure operation. Now, this is kind of a Skolem-Hall. But I define it in a somewhat different way. If you have a model and you have a subset of, you have an admissible A, you have an elementary submodel and a subset X, then the Hall of M and X is you take functions from M and evaluate them at points in X, or tuples in X. The point is, why do I bother with this? Is, well, you want to take Skolem-Halls, but you don't know in which structure. And here you don't have to know. I mean, so you basically want to take the Hall of M and X, but you don't know A, where it comes from. So you can do that. And basically, but you think of it as the Skolem-Hall. The important thing is that the Hall actually does not go, the rank does not go beyond M. So it's, you just take the models, X intersection delta, where delta is the supremum of the rank of M, and that's the Hall. OK, so we are going to fix an inaccessible cardinal and a bookkeeping function U. This is going to be our function which tells us which poset to use at a given stage. You can think of it as a Laver function if you like. And we use E for EV kappa and next for this. So now we define a class for each alpha in E. So basically, we're going to index our iteration not by all ordinals less than kappa, but only by ordinals in E. OK, it's not a big deal, but it's convenient. So, we want to define the collection of models we will use as side conditions at stage alpha. They won't be elementary submodels. Well, they will be elementary submodels, but not of V kappa, but of some elementary end extensions of V alpha. So, of course, V kappa is one of them. V kappa is an elementary end extension, but there are others. And this is important, actually. So here is the definition. Script A alpha is the collection of all admissible A's which are end extensions of elementary end extensions of V alpha and have the same size. The size actually is just in order to limit the number of models that we use at a given stage. OK, so let me speed up. So here is the structure. We will define P alpha for alpha in E together with the successors of E. And basically, if we have defined P alpha for some alpha in E, then we look at our bookkeeping function, U of alpha, and say, OK, does it give us a poset in our class? I haven't told you what is the class of poset. That will come from the theorem. I mean, you see what we need for the iteration to go through. If it is in the right class, we use it. Otherwise, we let Q alpha be the trivial poset. So P alpha plus 1 is just the P alpha star Q alpha. There is no. But the important thing happens for alphas in E. And both for alphas which are successors in E, I mean, but also limits. And notice that the way we set things up, well, the way I cannot notice because I haven't told you what the definition is, but we set things up in such a way that this whole iteration is uniformly definable in this structure. If we know E up to alpha, and we know the function U, then we can kind of uniformly define with parameter alpha. So inside any A in your collection of admissible models, A alpha, you can define a version of your iteration, which up to alpha agrees with the real one, and then it goes in its own way. OK, now let me describe the side conditions. The side conditions at alpha, now the main point is we want to have a real iteration. So at stage alpha, we want to use, we're going to go up to kappa. At stage alpha, we don't want to use all elementary submodels of V kappa because there are too many of them. Instead, we use elementary submodels of this model of these models in the script A alpha. Remember, they are small. They are elementary end extensions of models of V alpha of the same size as V alpha. So this is a small collection, and we're taking countable elementary submodels of those, and internally club. And here is the definition. I won't read it for you. Okay, well, I will read it for you. So C alpha is all countable model such that when you take their hull is in this class, A alpha. So, I mean, important thing is that it goes at least up to alpha. I mean, and U alpha are the internally club. And now this is the collection C alpha, and then there is C less than alpha, C less than equal alpha, and the same for U. So these are the models that we use at alpha. Now the point is when you put a model, you want to understand what is the impact it has at the iteration up to alpha. Now, here is a notion I call alpha isomorphism. Well, basically, the models are interchangeable to some degree. Here is the definition. So if you have two models in your class, C or U, you say they're alpha equivalent if when you take the hull of the two models with V alpha, well, now you get transitive, well, you may not get, it doesn't matter. You get some models. These models are isomorphic. The isomorphism is unique, and it maps M to N. So in particular, this is saying that, I mean, M and N are isomorphic, but they're more than isomorphic. I mean, there is an isomorphism morally that is the identity on V alpha. But you cannot quite say that because the models do not contain V alpha. So you just throw in V alpha to the two models, close, and then there is an isomorphism. It's clear that this is an equivalence relation. But as you go up, these equivalence relations become finer and finer, which is kind of clear. And the point is that for each equivalence class, there is a canonical model. And this is the reason why we introduce this. This is why we define this collection of models in this way. Namely, you give me a model which appears somewhere later. I'm going to look at its class, and I'm going to find a canonical representative. What is it? There is a typo. Let hull MV alpha. OK, so there is a V alpha, but you can see the next. So you give me a model and some alpha. I take the hull of M together with V alpha. Then I take its Mostovsky collapse. That's a transitive. And then I take the image of M by this collapse. It's the collapse not of M, but of M, hull of M and V alpha. And this is an alpha model, which is isomorphic to, it's alpha isomorphic to M. So this is the canonical representative. Now you check that this behaves nicely. Namely, if you take a model, if you have alpha, beta, gamma, you take a gamma model, you project to beta, project to alpha, that commutes. You could go straight from gamma to alpha. That's straightforward. Then you have a notion of membership. Now, in some sense, these models are they're not models, they're equivalence classes. But it happens that they have canonical representatives. So the class, so now when does a model, so I call it epsilon alpha. M is epsilon alpha n if there is a representative of the M alpha class inside N. Right, so it may be M itself is not in N, but there is something that looks like M up to alpha that is in N. And again, you check that this behaves nicely. If M is below alpha, it's contained in V alpha, that's just the membership relation. But it could be that you have that M is higher than N, but epsilon belongs to N, because its equivalence class has another representative which is below, that's all. And you also check that if you have alpha less than beta and you have two models at beta, if M is epsilon beta alpha, then its projection to alpha is epsilon alpha n. So this commutes with the projection. Of course, it does not necessarily go up, right? So if you have epsilon beta here, you project, you get epsilon alpha. If you have epsilon alpha, you don't necessarily get epsilon beta upstairs. Then you need the notion of intersection. Well, this is also a kind of, you think that if you think kind of morally, models are not really models, they're equivalence classes. So now I define this notion of intersection, which I call meet. So typically, you only need it in certain cases. If you have an Aleph-1 model, which is, in some sense, belongs to a countable model. Well, not necessarily belongs, but its transitive collapse, its real, actual Mostovsky collapse belongs to M. Then you can take M intersection with the transitive collapse of N and pull back to N. So there was pi, transitive collapse of N goes to N bar, which happens to be in M. You intersect. Well, remember, N is internally clubbed. So you're going to get the delta member of that chain, where delta is the omega 1 of M, or M intersection omega 1. And you pull it up. And now, can I have 5 more minutes? Or? Huh? I think I have 2 minutes, but I need just to give you the definition. So. OK, so then, so we have done, we've given all the definitions. The only thing, so one more definition, and that is we have to say, we're going to have a bunch of models floating around, and at a given stage, we're not going to look at all of them. We have to see what are the models that are relevant for us at that stage. And this is what I call a model is being active at a certain stage alpha. In other words, when this M should be considered at alpha. Well, you would like to say if alpha is a successor point of E, then the predecessor should be in M. Or if alpha is a limit, then M is cofinal in alpha intersection E. But there is a glitch. I mean, it's not quite that. So you have to throw in omega 1. So for the Aleph-1 models, the definition will come in a moment. For countable models, you throw in omega 1 and close. So the countable models now become of size Aleph-1. You throw in omega 1 and take the half. And now here's a definition of what it means to be active. You say that M is active at delta if I try to be kind of, terse here. M of omega 1. But remember, M of omega 1 is, if M is size Aleph-1, it's just M. If M is countable, you enrich it. You put in omega 1. So if M intersection E intersection delta is cofinal, but this means that if delta is a successor point of E, then you have the predecessor. But not necessarily in M. You have it in M of omega 1. And this actually creates a problem. So this is the first attempt to the pure side condition process. So it's a kind of straightforward, well, a little bit less straightforward generalization. So what are the conditions in M, boldface M alpha? Well, they're finite chains when you use the models up to alpha, up to and including alpha. And for each delta below alpha, including alpha, the relevant model, the active models, are an epsilon chain closed under meets. And the extension is basically, if you think about it, you don't want to say inclusion, reverse inclusion. No, because a model is actually appears at some stage. You should be allowed to move to a higher stage and replace that model by something that projects to it. And this is the OK, so this almost works, except there is a glitch. And I think I don't have time to say, but you can, this adds an extra complication, which maybe if people are interested, I can explain. And this complication can be avoided if you don't use all uncountable models, if you internally club, if you use what Matteo calls guessing, do you call them guessing models? Yeah. But of course, you need to be in a universe of set theory where you have enough guessing models. So now you can define the, let me just put the slides, the definition of, right, so there is a complicated definition which I call star, which I don't have time to explain, which basically says that things, somehow morally, you have a countable model, and if it has some stage where it was active, but because it's not in the model, but it was in M of omega 1 of the model, then somehow M should see that, have some control over that stage. And that's this complicated condition, which I think we should skip. And basically, you get this, and you get basically the side conditions as you would like. It has exactly the same property as the ones we had before. And now you can define the iteration. I think I will stop. Let me just put the definition of the, the definition of the pose set, the iteration. And then you add the working part. And basically, we've done things in such a way that it's straightforward to prove. I mean, as I said, the main point is the definition. OK, thank you very much. Yes.
Can you move to the slide of applications?
Well, yeah, but the applications are not, this was just the applications of the pure side condition. It's basically rewording some of the known results. In Bill's I of omega 2 is the trivial on S omega 1, omega 2, and Urey-Abraham's Aleph, model where the Aleph 2, Aleph 3 simultaneously have the 3 property. That's just the pure side condition. You can do these things. So that's already something non-trivial, right? But then of course, we're going to add the working part, and then